Good afternoon, calculus class today. So just want to record a video for 1.6. Again, this one is for calculus, James Stewart, section 1.6, the last section of chapter 1, inverse functions and logarithm. So you guys do remember now the one-to-one functions. So anytime that we do have a graph like this, and you want to find out whether the function is considered one-to-one, so that means we have to go through the horizontal line test. So what that means is that the horizontal line, if the line touches the graph at one point only, so that means the function is considered one-to-one. So now let me show you one of the example here. So the graph on the left-hand side here, so let's say that we do have a horizontal line. Okay, let's just use a dotted horizontal line here. So let's say that you want to make the line going through the graph here. Doesn't matter where you want to draw the line. You can put it right here above the x-axis, right here on the x-axis, or down below the x-axis. As you can see that the line only touches the graph at one point, so that means the function is considered one-to-one. So the first one, yes, it is one-to-one. And now what about for the second graph right here, the one on the right-hand side? Once again, you want to make the line going through the graph. Okay, so again, horizontal line test. So anywhere, but you probably want to put the one that you'll see that the parabola is going through. So here's what I put in the line. So it looks like, well, it's not just considered one point of intersection with the line of the parabola, but also here's another one. So this one, since the graph, it fails the one-to-one, the line test, the horizontal line test. So that means it's not one-to-one. Okay. So now determine whether the following function are considered one-to-one. The things that you can always sketch the graph, or you can always just put in the parent functions or the parent graph for the function. So this one you don't really have to sketch the actual graph of the function. You can just put in the parent function. So the first one, as you may notice, it's considered quadratic. So quadratic functions, so the parent graph is always considered a parabola. So if the parent function is passing through the the line test, the horizontal line test, so that means it's considered one-to-one. But the parabola, we just did that earlier. So this one, it fails the one-to-one, the horizontal line test. So that's why it's not considered one-to-one. Again, if you just draw the line here, so again, the graph and the line, you'll see that we do have 2 points of intersections. So the first one, it's not considered one-to-one. And for those you might be wondering, what happens to the one-to-one function? Well, if the function is not considered one-to-one, so that means its inverse, it's not considered a function. So notice, so if the function is not considered one-to-one, so that means its inverse, it's not a function. So that one, the inverse will be just like a relation. Okay, we'll take a look at that. And here's another one. So the parent graph for this one, we do know that it's considered rational. So again, this one is just the exact same parent graph. So try to draw the graph here. That's what we talked about before for the transformation. It's just like the volcano with the vertical asymptotes right here in the middle. So it's going this way, going this way. So again, this one, it's not considered one-to-one. So by the time that you draw the horizontal line test, not the vertical line, but the horizontal line test. So you can see that the line touches the graph at 2 points. So this one, it's not one-to-one either. Okay, so the first one, no. The second one is also no. And what about for cosine of x? Is that considered one-to-one? Again, cosine, we do know that it's a bell curve. So that one, if you just make the horizontal line there, so also it's not considered one-to-one. Again, cosine is going this way. It's an upside down bell curve. So this one, once again, so try to make the horizontal line here. As you can see that the graph here and the line, so, and we do have 2 points of intersections. One that's over here, here's another one. So this one, no, it's not one-to-one. Okay, so now let's move on to the next one. So given that f of x equals 2 plus x squared plus tangent pi x over 2, so where negative 1, it's less than x, it's less than 1. So you want to find the inverse of 2. Again, anytime that you want to find the inverse function, so that means we want to switch the variable x and y. So in other words, that in order to find the inverse, so we can always swap those x, y values, okay? So what this one is showing that the y value is given, which is 2. So what we need to do here, in order to solve for x, we just want to put in 2 equals 2 plus x squared plus tangent of pi x over 2. Well, this one's supposed to be 2 right here. So what we can do on the function, we can just bring everything together to one side, and then basically we can just solve for x. So what this one is saying that, so 0 equals x squared plus tangent of pi x over 2. So for this one, we can put in the functions y1. So it's a calculated problem. So y1 equals x squared plus tangent of pi x over 2. And then from here, we can find the x-intercept. So two ways we can do it. We can use the decimal. We can use that the graphing calculator. So I'm going to show you both. Okay, so let's see. So I need a graphing calculator here. Okay, so let's see this one, the TI-84. So while this one is loading, so let me show you that on the decimal first. Okay, so it's easier to put it in the function with the decimal. You can find the x-intercept, y-intercept very easily. So again, y1, so you want to set that y equals, again, the function we have, the one after we simplified it, it's x squared plus tangent of pi x over 2. So x squared, x caret, and then bring down the cursor, plus tangent of parentheses, pi x over 2. So for pi, you want to type in pi, or just use that the keyboard right here if you want to. So pi x over 2. And we want to put in the restriction because the domain for this one is from -1 to 1. Okay, so go to the 2 bar here. So again, x-axis, change the window, the setting. So -1 all the way to 1. For the y range, so for the range, the y-axis, no need to worry about it, just leave the way it is. And now, and simply press the 2 bar again. So if you just want to find the x-intercept, so we do have one position here, which means that x equals 0. So for this one, if you want to find out the value, so that means y1, well, if y1 equals 0, so that means x must be 0. So for f, inverse of f of 2, so that would be considered 0 here. So in other words, what this one is saying that if you plug in 0, so that means f of x is 2. Okay, so in other words, so let's say that you plug in 0 for f of x, so it turns out to be 2. So this one is just another way to rewrite it for the inverse. Again, if the inverse notation is given, that means we have to swap the xy value. And now let's try another one like this. So the other function we have, it's g of x equals 3 plus x plus e to the power of x. So again, inverse of g of 4. So that means for the y value is 4. So we plug in 4 for g of x, and now we want to solve for x. Now before you solve for x, you want to bring everything together to one side, so subtract 4 both sides here. So we do have 0 equals 3 minus 4, then that'll be -1 plus x plus e to the power of x. Again, try to use decimal for this and then find the x-intercept. Again, I'm going to show you how to do that on the TI-84 in a minute, but let's just do that with the decimal. So clear. So the other one we have is y equals -1. So y equals -1. Okay, so this one, there's no need to put in the range here, so we didn't finish putting the whole function, so let's see. And the one we have is -1 plus x plus e to the power of x. So plus x plus e to the power caret, it's -x. Okay, making sure that we're putting the, e to the power of x, not -x. There's no reflection here. Okay, so as you can see that, so here's the functions. So once you solve for x, so that means this point here, it's also what? 0, 0. It's not just the x-intercept, but also it's the y-intercept. So for this one here, so that means for x, we do have x equals 0. For g inverse 4, so that would be 0. And here's the way you can check the word. So plug in 0 back to the original function. So we do have 3 plus 0 plus e to the power of 0. So 3 plus 0, that's 3. E to the power of 0, that's 1, which is what? 4. So that's the way to check the word. So once you find out the x value, so plug in that number back to the original function, and then try to verify it and making sure that it's considered a given y value. And now, for those you might be wondering, how do I put it into the graphing calculator for example 2? So again, the function we have is what? X squared plus tangent of pi x over 2. So the TID 4, okay, wait, right here. Okay, so let's go back to the normal screen here first. So second quit. So once you turn on the calculator, it's all blank, unless you have put in something into memory. And now y equal, so this one we just want to clear that off. And also I can show you that the key history here at the same time. So again, the function that we just simplified it, which is what? X squared plus tangent of pi x over 2. So x squared okay, so x caret 2, bring down the cursor, plus tangent of pi x over 2. So tangent, right here, pi x. So you want to go to second caret pi x divided by 2. Another thing that you need to make sure here, because this one we're dealing with the trig function, it's not just considered algebraic, but also it's what? It's trigonometric. So that means for the mole, instead of using degree, so you're using radian. So make sure that radian, you got to be highlighted. Okay, radian. So go down to radian and then press enter. Mine is already in radian, but I just want to show you that how to convert it from degree to radian. And now another thing that I need to change here is the window. Instead of going from -10 to 10 or -infinity to infinity, this one, the given domain, it's -1 all the way to 1. So x min is -1, x max is 1. And then once you're done with this, just hit graph. So again, this one is showing that the whole perspective of the graph from -1 to 1. Now it's not the inverse function, it's just the original function. But we just put in that y equals the value of y equals 2. And now as you can see that here, so for the x-intercept, it's 0, 0. Another way to make sure that the x-y-intercept, so we can always go to second trace, 0. And now the calculator is asking about the left bound. And I'm sure that for this one, I showed you that for the previous lecture, or one of the video that I put out for the using calculator, finding x max, x min, or the y min, y max, or the x y intercept. So left bound, so it's somewhere down below the x-axis. And then for the right bound, so somewhere it's right above the x-axis. The reason why that I put it this way, because this one, it's an increasing curve. So that's why the left bound, it's down below the x-axis. And the right bound, it's right above the x-axis. And now you want to press enter one more time. And here we go. 0, 0. So for the other one, you pretty much want to do the same thing. So put in that functions. So -1 plus x plus e to the power of x. And then you want to find out the x or the y-intercept. Okay, so now let's move on to the next one. Now, what's the general way to find the inverse? So anytime that you want to find the inverse, so two things that you need to do. So you want to switch the xy variable. Okay, excuse me, let me just rewrite it. So switch x and y. So after you switch that x and y, so that means you want to solve for y in terms of x. And then the last thing, well, this one basically just want to rewrite the function as what? Inverse of f of x. So rewrite that y as inverse of f of x. Okay, so now let's do the first one. So we swap the variable first. So we do have x equals natural log of y minus 2. And now from here, we want to solve for y. And for those who might be wondering, can I distribute that natural log sign? There's no such property for this. So what you need to do, you want to take the base e on both sides. So e to the power of x, so that equals y minus 2. So one thing that we notice, e to the power of natural log, it's always 1. And now from here, solve for y, so we do have e to the power of x plus 2. And for those who might be wondering if we do realize that, so from the natural log functions, once we find inverse, so this one is just considered the exponential function. And don't forget about the last step here, so make sure that rewrite it with inverse of f of x. Again, that -1, it's not the exponent, it's just the inverse indicator. So this one is just the indicator of an inverse function. And then for the other one, it's quite similar. So let's take a look at that. Again, we want to follow those three general steps here, and then we can find out the inverse. So again, first thing that you want to do, so you want to swap the variables. So we do have x equals e to the power of y over 1 minus 2e to the power of y. And now for those who might be wondering, there's nothing we can do here, but don't forget, this one is considered proportionality. So what we can do, we can actually cross multiply them. Okay, so what we got here is x times the quantity of 1 minus 2e to the power of y. And then the other one, it's just e to the power of y. Again, so what I'm doing here, it's just cross multiplying. And now keep that in mind, we want to solve for y in terms of x. So the way to solve for y in terms of x, so any kind of y term, so that means you want to collect them together. So before you do that, you want to distribute. So we do have x minus 2x e to the power of y. So that equals e to the power of y. And now for the e to the power of y, anything that's considered y terms, so you want to collect them together. So we do have x equals 2x e to the power of y plus e to the power of y. And then what I can do next, I can take out that e to the power of y because that's the greatest common factor, the GCF. And now what's left here, we do have x equals e to the power of y times 2x plus 1. So in other words, so x over 2x plus 1 equals e to the power of y. Again, y, that's what we need to isolate, but there's a base e here. So how do we get rid of that base e here? So basically, we just take the natural log both sides. So eventually, so it's natural log of x over 2x plus 1. And then, so that equals y. And also for y, I can put that as the inverse of f of x. Okay? And for those who might be wondering, is there any other way that we can rewrite the natural log here? Well, we do know that the quantity is considered a quotient. So this one, we can just put it in as natural log of x minus natural log of quantity 2x plus 1, using the property of natural log. But normally, we can just leave it like this. And that's the inverse function. Okay, so now let's see what else that we have. So for the rest of this, it's about using the properties of natural log. So a couple of things I would like to go over here. So the product, there's some kind of a special property for the natural log and log. So they're pretty much the same kind of property. So let's say that we do have a product. So let's say like log of x times y. So that means once you expand it, it's log of x plus log of y. So it's a product to sum. And here's another property. So what about, let's say that x and y, they consider a quotient. So the way that we expand it, so it's log of x minus log of y. So this one is called quotient to the difference. And then here's another one. So let's say we do have a power r. So anytime I see the power with the log or the natural log, you can always bring that power to the front. So that means we do have r to the power r times log of x. And then here's another one. So let's say we do have log of base b x. And this one we can always rewrite it with the change of base formula. It's log of x over log of b. And for those you might be wondering, wait a minute, there's no base here. If the base is not shown, that means it's always considered 10 for log. So log base 10 of x over log base 10 of b. So now using the property to verify to simplify the following, the logarithmic expression. Okay, so now let me change the color of the pen here so you guys can see and follow through better. Okay, let's see, let's use red. So log of 3 and 81. So another way that I can rewrite it, this one can be considered a log of 81 over log of 3. A lot of people might be considered doing that. Well, certainly you can do things like this, but here's the other simple way to do it. So since we don't know what that is, we can always set that as x. And now we can convert this one back to the exponential form. So the base is 3, the result is 81. In the power, it's x. So in other words, so it's 3 to the power of x equals 81. So that means x is considered 4. So 3 times 3 times 3 times 3. So multiply 3 4 consecutive time. So it's what? 81. And here's another one. So since we don't know what that is, so this one is written as 3 to the power of x, but it's considered 1 over 81. So that means x is negative 4. So the negative exponent, that means we need to convert the number with the reciprocal. And now the rest of this, we want to condense them. But before you condense, make sure that they do have the exact same base. So 2, 2, and 2. So for the first two terms, it's considered a quotient because that's a minus. So minus, it's a difference. So it's corresponding to quotient. So this one can be written as log base 2. So 27 over 3. And then the third term, it's a plus. So that means it's considered multiplication. So sum to product. So multiply by 10. So 27 over 3, that's 9 times 10. And that would be considered 90. So log base 2 of 90. Okay, so again, quotient, difference to quotient, and then sum to product. And now what about natural log of e to the power of e to the power of 10? So one thing that we notice, natural log of e, it's always considered 1. Okay, so the one that we use for solving the inverse. And e to the power of natural log, it's also considered 1. So one thing that we can just cancel here is that natural log of e, so that just considered 1. So what we left, the power, we can always bring it to the front. So this one is just e to the power of 10. So what we got right here, it's natural log of e to the power of 10. Again, natural log of e, that just considered 1. And then the power, we can always bring it to the front. So eventually, the result is considered 10 times 1, which is what? 10. Okay, so now let's see what else that we have for the rest of this. So sketching the following functions with log of base 10 of x plus 5. So this one is something we talked about in the packet already. So anytime that you deal with log, natural log, we always put in the transformational form. So y equals a times log base b of x minus h plus k. Again, a will be considered the scalar, which is considered either the vertical stretch or horizontal stretch. If a is greater than 1, so that means it's a vertical stretch. But if a is less than 1, greater than 0, it's a horizontal stretch. But another thing that we need to notice, if this one is negative, that means the graph is going to be reflected over the x-axis. So let's say a is less than 0. It's a reflection over the x-axis. Okay? So let's say that there's a negative right in front of the variable. That means it would be considered reflections over the y-axis. Okay, so now for this one thing that we can identify, it's 1, so that means the curve is going to be considered normal shape. The base is 10. And then another thing that we notice, h is what? Negative 5. And then k, if k is not shown, that means it's 0. Another thing involved with this is the vertical asymptote. If that's a logarithmic function or natural log functions, the value of h, it's always considered the vertical asymptote. So the value of h is negative 5, so 1, 2, 3, 4, 5, which is over here. So the VA. And we do know that the base is 10. So now, in order to get some point, we can always set up the XY table. So in order to find out the easy number for x, so we need to come up with the exact same number, the same quantity as the base. So for x here, we probably want to use 5, because 5 plus 5 is 10. So log base 10 of 10, then that'll be 1. So 5, 1. So we got 1, 2, 3, 4, 5, 1 right here. Okay, so another number that you would like to use. So let's say this one, it's considered 1. So 10 to the power of 0, it's always 1. So let's say x is negative 4. So negative 4 plus 5 is 1. So log base 10 of 1, guess what? 0. So negative 4, 0, right here. And then for the graph, all you need to do, just connect them. And then try to extend it all the way through. And for those, you might be wondering the domain for this one. So the domain for this one is from negative 5 all the way to infinity. And then the range for this is from negative infinity to infinity. And now, what about for natural log of absolute value of x? So again, it's under the same kind of structure, y equals a, but instead of being log base b, it's natural log of x minus h, quantity, plus k. So for a here, it's considered 1, h, 0, and then k, it's also 0. Now, one thing that we notice for natural log of x, so natural log of 1, it's always considered 0. So let's say that I try to use the xy table without the absolute value. So just saying that it's natural log of x for the parent function. So for natural log of 1, it's 0. Another thing we notice, natural log of e, which is considered, well, it's about 2.7. So natural log of e, it's 1. So 1, 0, and then 2.7, 1, right up here. Again, the VA, it's always the value of h. So the dotted line here is just the y-axis. So that means eventually the graph is like this. Well, this one is just a parent function. It's just the parent graph. So that's why I need to use the dotted line for this, not the solid. So let me fix this. Undo. Okay, so let's just using dotted line for the parent function. So this one normally, the graph looks like this. Now, but another thing that you need to watch out here, this one is just the parent function. So for the absolute value, that means we're making all the x value positive. So which means that the other side, whatever that we have for the x value, for the negative, we can also put in the reflection. So once you do the absolute value, this one is considered y equals natural log of positive negative x. So what this one is saying that positive x, so we just satisfy the parent function. But for the negative, again, the negative, if you see the negative sign right next to the variable, so anytime they see something like this, so that means there's a reflection over the y-axis. So besides the positive here, so we do have another one, the negative. So that means the other part of the graph is going to be like this. So kind of like a volcano again, but the thing's that it's being upside down. Again, this one is also the positive. So we need to put in this one as well. So one is going this way, the other one is going to the other side. And once again, they're both considered symmetrical. And for those you might be wondering the domain for this one, so it's negative infinity to 0, union 0 to infinity, and then the range. So what do you think the range is? The range is always consider all real number. All right. Okay, so now let's see. And the rest of this, we just want to solve for x by using the property. So again, the way to isolate the variable, so this one, f5 both sides. And then take the natural log both sides, because you cannot do any addition, subtraction, multiplication, or division. So natural log of e, that's just 1. So 1 times the power, just that power, 2x minus 3. Natural log of 5, we don't know what that is. Just leave it. And now, in order to isolate the variable, so we just add 3, then divided by 2. So natural log of 5 plus 3, and then divided by 2. Again, this one is considered an irrational number. So that's it. And now what about for this part right here? So we do have natural log of x, and then natural log of x minus 1. So this one, basically, we can condense them. So we got natural log of x times the quantity of x minus 1. Again, the property that we have, the one that I put in previously, so this one we can go back and forth. We can always go from product to sum, from left to right, or we can go from right to left. Sum to product, condensing. So that equals 3. Again, this one is considered natural log of this whole quantity. So in order to get rid of that natural log, we take base e both sides. So we do have e to the power of natural log cancel, because that's just 1. So we do have x squared, and then the other one here, minus x, and that equals e to the power of 3. And for those you might be wondering, how do I solve for the rest of this? Well, this one, again, e to the power of 3, it's just considered a constant. So that means we can bring everything together to one side, because the whole thing is considered quadratic. And then from here, we can use the quadratic formula. So A, it's 1, B, it's negative 1, and then C, it's e to the power, negative e to the power of 3. So you want to put it into the quadratic formula, so you can just solve for x. And now, what about for natural log of x equals 1? The left-hand side, it's considered composition. So the way to do it, so take that e on both sides. So again, e to the power of natural log is just 1. So we do have natural log of x equals e. And then in order to get rid of that natural log here, we just take base e. So that means x is considered e to the power of e. And now what about for the inequality? So for the inequality, the compound inequality, so basically we just want to take base e for each term. The one on the left, the one here in the middle, the one on the right. So we do have e squared, it's less than x, it's less than e to the power of 10. That's it. So again, for b, you want to use the quadratic formula for this. So again, the quadratic formula, which is negative b plus minus square root of b squared minus 4ac all over 2a. So we can finish that one. Okay, so now, and the rest of this, we do have the trig function, inverses of trig function. So, and I'm sure that this one is something we talked about for the study packet already. If you guys just recall the study packet you guys turned in on Friday. and the inverse trig functions, finding the radian with the ratios, things like that. But one thing I just wanted to recall here, it's the unit circle. So unit circle, we always started at 0 or 0 degree, 0 radian. Up here, we do have pi over 2 or 90 degree. And then over here, pi. And then down here on the bottom, 3 pi over 2. So there's another video for that if you guys want to refresh that, the unit circle. So you're more than welcome to watch that unit circle I put in for the instruction. So this one, unit circle, the radius is always 1. So that means the position here is considered 1, 0. And then all the way up here, it's considered 0, 1. And then back down here, it's considered -1, 0. Down here on the bottom, 0, -1. And now inverse of cosine of 1. Anytime that I deal with cosine, that means it's considered the corresponding x value. Okay, so cosine, it's always considered the corresponding x value. And then for sine, it's always considered the corresponding y value. And what about for tangent? Tangent is just the ratios of y over x. Okay, and then cotangent is the corresponding value of x over y. And then for secant, so secant, it just consider r over x. Okay, again, this one, it's all about the ratio. And then cosecant, it's all about r over y, the radius over the y component. So now inverse of cosine of 1. So in order to find out that, so 1 is over here. So there's only one position showing that inverse of cosine of 1. Unless you want to go around the unit circle more than once, so you do have a multiple solution. But since you go around the unit circle from 0 to 2 pi, so we only got one solution for this. So that means the radian is 0. Again, you can put in 0 radian or 0 degree. But it's better for you to put in radian because we're using that, the ratio. And also sometimes we have to put it into the calculator with the function. So what about inverse of secant? So this one is showing that 2, but it's not just 2, it's 2 over 1. Okay, again, the radius, it's 1. Okay, but the thing is that it's inverse of secant of 2 over 1. So secant is not really showing on the unit circle here. Another way you can just analyze that secant. So secant, so let's say we do have a ratio. So let's say that we do have a 30, 60, 90 degree. So the ratio is always considered 1, root 3, and 2. So this one is showing that as 2 over 1. So that means for secant, it's considered what? 90 degree. So 90 degrees, so that means it's showing that it's pi over 2. Well, but the thing is that if that's pi over 2 for secant, it's actually considered undefined. Okay, so this one, the radius, if that's greater than 1. So it looks like this one does not exist. But now let's take a look at that one more time. So another way that you can analyze that, this one is considered inverse of cosine. It's 1/2. Okay, got to be careful. So inverse of secant, we do know that cosine and secant, they're just like reciprocals of each other. So another way we can analyze it, we can put in inverse of cosine. So inverse of cosine is 1/2, so that means it's in the first quadrant. So 1, which is the radius, and then hypotenuse 2, and then the height here, it's considered root 3. So for this one, you can say that this angle, it's considered 60 degree. If that's 60 degree, so that means it's considered pi over 3. So pi over 3. Well, what else could that be? So this one, it would be considered negative, negative. So if that's negative, negative, so that means, well, radius cannot be negative. So that's the problem. Radius is always considered positive, so that's why you only got one solution here, pi over 3. Okay, so now what about for arctangent? So arctangent is considered sine over cosine. So again, the ratio for that for tangent is y over x. So this one can put in 1 over 1. So again, 1 over 1, so that means this one is appearing in the first quadrant. So instead of being 30, 60, 90, so the other special right triangle we have is 45, 45, 90. So 45, 45, and 90. And the ratio for that is 1, 1, and root 2. So again, positive, positive for y and x. So that means it's in the first quadrant. Okay, so opposite, it's 1. Adjacent is 1. And the hypotenuse is root 2. So for that angle, for this angle here, it's considered 45 degree, which is pi over 4. And then what about something like tangent of r cotangent of x? So let's just put in analysis. So for that ratio, x is considered x over 1. So again, with the unit circle, we do have x over 1 in the first quadrant. So again, I need to erase all this. Okay, so cotangent is considered x over y. So for this one here, so that means it's x. Here's 1. Adjacent over opposite. Well, for those you might be wondering, what about the hypotenuse? Hypotenuse, we can use that the Pythagorean theorem. So square root of x squared plus 1, or 1 squared, which is the same thing, square root of x squared plus 1. So anytime that you want to take the inverse of cotangent, inverse of secant, inverse of any trig function, it's always considered the angle here, theta. So basically what we need to find out here is tangent of that angle in the first quadrant. So according to the ratios of tangent, it's considered y over x. So which means that it's considered 1 over x. And that would be the final form. Okay, so now let's see what else that we have. Okay, so more. So what about sine of inverse of tangent of x? Again, the ratio given here, it's x over 1. So positive, positive. So that means the triangle, it's appearing here in the first quadrant. Excuse me. So tangent, it's considered opposite over adjacent. So it's x over 1. Again, this one, it's always called the base angle, theta. So this one can be written as sine of theta. So sine of theta, it's considered opposite over hypotenuse, or y over r. Okay, so y here, it's just x. And then radius, we need to figure out what that is. Again, using the Pythagorean theorem with that 1 and x. So we do have square root of 1 plus x squared. So it's x over square root of the quantity, 1 plus x squared. And for those you might be wondering, do I need to rationalize it? It's up to you. So you can just leave it like that, or you can just rationalize it. So it's just multiply the radical, top and the bottom. So x times square root of 1 plus x squared over 1 plus x squared. Okay? So sine, opposite over hypotenuse. And now what about for this? So this one is quite similar. So you might be wondering, what about the 2 right there? That's kind of confusing. So we'll deal with that too later. So again, anytime that you take the inverse of any trig function with the ratio, it's always considered the angle. So for this one, inverse of tangent of x, so showing that it's in the first quadrant again, opposite over adjacent. So hypotenuse, it's always the Pythagorean theorem, which is x squared plus 1, and then square root of the whole quantity. Okay. So once you take the inverse of this, again, going back to that theta, and we do know that it's a double angle. So double angle, we can use either one of those identities. So cosine of 2 theta, we talked about this formulas already. So it could be either written as 1 minus 2 sine square of theta, or 2 cosine square of theta minus 1, or cosine square of theta minus sine square of theta. So it depends on which one that you prefer. Eventually, it's going to be the same thing. So we do know that, well, let's just use the first one. So 1 minus 2 sine square of theta. So it's 1 minus 2 times sine of theta, which is considered x over radical of x squared plus 1. So x over square root of x squared plus 1. And then square the whole thing. And then the rest of this, you just want to multiply it out. So 1 minus 2x squared over x squared plus 1. And definitely you can put this all together. So combine them together. So we do have x squared plus 1 over x squared plus 1 minus 2x squared over x squared plus 1. So combine them. So we do have x squared minus 2x squared, which is negative x squared, plus 1. Just leave it all over x squared plus 1. And that would be the ratio for cosine of 2 theta, or cosine of 2 inverse of tangent of x. So again, the better way for you to set up the ratio with the inverse, so just draw the diagram here. So once you draw the diagram, it's clearly showing that the ratio, opposite, adjacent, hypotenuse, base angle. So I think that's pretty much about it for this lecture today. And you're more than welcome to fast forward or just rewatch this video, especially for the content that you're kind of confused or you need more time to understand the structure. All right, so I'll see you guys next time. Take care.